Hi, my name is Lena Stubbemann. Together with my co-authors, Dominik Dürrschnabel and Robert Refflinghaus, I would like to present a new semantic gaze analysis approach. Our method relies on neural networks and is especially suitable for eye tracking experiments in three-dimensional, virtual, augmented and mixed reality settings. How come we research in this topic? Today, virtual reality and augmented reality technology is increasingly combined with eye tracking. Thereby, in many applications, the essential question is, which objects or which features are participants looking at? Answering it, however, often remains a resource-intense task, especially when it comes to user-specific three-dimensional scenes. So far, this has been an obstacle to economic use, so our goal was to change that. When it comes to the state-of-the-art, existing approaches can be divided into three groups: manual and burning shape approaches, tracker and model-driven approaches, and computer vision and data science approaches, which we account our approach to. As in this group, we see the highest potential to develop a one-fits-all solution over the whole XR range. However, one main limitation which comes with this approach group is the availability of suitable annotated databases. This is especially critical when non-standalone volumes of interest are to be annotated. This is because the granularity of pre-annotated databases is often restricted to delimited objects such as cars or trees, and not, for example, to objects dumpers or objects levers, buttons. To overcome this problem, our approach includes a method to build suitable databases from scratch almost fully automatically. Therefore, our main contribution are as follows. First, we show how arbitrary new training data sets for the annotation of volumes of interest can be built up fully automatically doing image augmentation with SIGCHI. And second, we present a machine learning approach to automatically annotate VOIs at a feature level and only on the basis of synthetically generated training data. To do so, our approach consists of four main steps, which I am going to explain now. In the first step, we use a virtual model to prepare our training data. To do so, a marker is created and systematically moved across the surfaces of each volume of interest. This is done by defining a moving path for the marker. The resulting simulation is then exported as frames and cut into thumbnail size around the position of the fixation marker, as can be seen here. To make those training data suitable to the actual experimental scene, while avoiding intense simulation efforts, we then perform an image augmentation. Thereby, we perform a channel shift to transform the simulation data into images that appear to look like the desired target domain. To build a target domain, we again add a marker, but this time to experimental data frames, and again cut those frames into thumbnail size. Here you can see how the channel shift is performed. To do so, we use a generative adversarial network called SIGCHI. This architecture can be used to translate images between two different domains in the absence of paired examples. In our case, SIGCHI translates images from the domain of the simulation data, which is our source domain, to the domain of the artificial fixation data, which is our target domain. The channel shift can be seen here as it goes from A to B. Performing the channel shift, we now have a suitable synthetic set of training data which we can next use to train our classifier upon. For this, we use a convolutional neural network called ResNet. At last, we can now use the so-trained classifier to predict the volumes of interest of our experimental data. We do so by classifying every frame of the gaze replay which contains a fixation. We then perform a popular vote over all frames to determine the overall volume of interest result. To evaluate our approach, we tested our method in two experimental design studies on coffee machines, one being a real-world setting and the other one a virtual reality setting. VOI annotation was done on a feature level with 10 different VOIs that can be seen here. As baseline, we used IC3D, a geometrical model-driven approach. As ground truth, we relied on manual annotations. When it comes to the tracking apparatus, we used SMI mobile eye tracking classes, and for the fixation detection and the creation of the gaze replays, we used bgaze 3.7. To fulfill the technical demands of our baseline IC3D, we furthermore needed an SMI 3D60 head tracking system and an outside-in motion tracking system, which was OptiTrack Prime X13W. When it comes to network training, we used a thumbnail size of 224 × 224 pixels. For image augmentation, we used the SIGCHI architecture as proposed in SU and a training dataset of 1000 images for each domain. When it comes to the CNN classification, we used the ResNet 50v2 architecture as proposed from HE, with an output layer of 12 neurons, which is 1 neuron per VOI and 2 additional ones as default classes. Training data here was 100,000 artificial images for each domain. As training parameter, we used an Adam optimizer, a learning rate of 0.001 over 20 epochs, and a sparse category cross-entropy loss. The results of the experiments can be seen here. As you can see, overall, our approach performs slightly better in virtual reality than in the real world. This is expectable as the simulation data resembles the virtual reality optics better. Still, our approach can compete with IC3D, as both approaches reach comparable results, as can be seen in this comparison. Looking into the proposed process in details, we furthermore asked ourselves, first, is it reasonable to use simulation data instead of pre-experimental data as a training basis? And second, how big is the performance share of the image augmentation? To answer the first, we looked at 30,000 pre-experimental images, which then needed to be annotated manually, and trained a new ResNet classifier upon it. The results can be seen in this line. With the generation of the databases taking around twice the time of our approach, the results show that the databases were still not broad and precise enough to train a complex neural network such as ResNet. Our approach can thus be seen as economically more viable, as it achieves a much higher accuracy at lower time input. When it comes to the performance share of SIGCHI, we trained the ResNet architecture exclusively on unaugmented simulation data. The results can be seen in this line. As you can see, SIGCHI is boosting the accuracy tremendously, and this is true for both settings. Using the image augmentation seems to compensate the reality deficit of pure simulation data sufficiently. Overall, our work should therefore be seen as proof of concept for a new method to annotate volumes of interest in interactive three-dimensional settings, which reaches state-of-the-art accuracy while allowing cross-platform use. For a deeper discussion, please refer to the paper. Thank you for your attention.